Hello all, welcome to the new lecture of this course. And so far we have done the modeling of the induction machine, particularly squirrel cage induction machine in the rotor flux oriented frame of reference, where we have obtained the equations in the DQ frame of reference for the voltage on the stator, and also we have derived the correlation between the stator current and rotor flux magnetizing current and the slip speed. We have also given equation for the mechanical model of the system of the drive, and eventually we have come to these five equations who are defining the electromechanical modeling of the machine. Now the same thing we have represented in terms of block diagram, and what we are finding over here is that the stator current ISD and ISQ are primarily dependent on the supply voltage VSD VSQ. However, the rotor flux magnetizing current IMR is basically derived from ISD, and IMR is eventually used along with ISQ to realize the torque in the machine with some constant KT, and then that results into the speed in the drive. And we can use IMR and ISQ to come up with the slip speed, and in combination with the mechanical speed we can realize the synchronous speed of the machine. So this is in a nutshell we are having the as a model of the induction machine. Now we are trying to apply some controllers for torque and speed control of this system. So eventually this is also called as vector control of CIM or rotor flux oriented control of So there are different terminologies, and we understand what's the reason behind these terminologies. So we would go ahead with the design part of the controller. Now in this block diagram, essentially what we are trying to have is we are trying to have the mechanical speed controlled dynamically in a manner what we understand. So when we are planning to have control on any quantity, it is going to respond on basis of certain reference given to the system. So we are going to have, say, a reference given omega m star for the system, and this once again we are going to use our feedback based control for having the good dynamic performance. So we will have the feedback of the actual mechanical speed, and the error between the reference and the actual speed will be processed through a PI controller. It can be processed through a PI controller. Eventually this PI controller would generate the cause which is affecting the change in speed. So it is affected by the torque, which is eventually dependent on ISQ. So which is why we would be generating the reference for ISQ over here. So I am marking it as ISQ star. Now once again, going by comparison of this feedback of ISQ, and error can be fed to one more PI controller can be kept over there for the current control, and the output of that PI controller essentially would generate the voltage command which is going to affect the ISQ. However, in this model, if we see that once we are applying the voltage on the machine, we have certain nonlinear components indicated over here. These are appearing on account of the cross coupling and something which is representing the back EMF in the machine. So these nonlinear terms must be compensated in advance through feed forward components to make the system linear. So which is why we do have the feed forward compensation, and when I say compensation, it essentially means that if the term is having a negative sign, it is getting subtracted from the actual voltage. We need to have addition of the same in the reference signal. Now, as I said, we are adding these terms to the reference signal, which is eventually going to get multiplied with the gain of the inverter to generate the actual voltage. We need to scale these terms also with respect to the gain of the inverter. Now, the output generated by this combination is basically going to drive the system for generating the desired voltage at the machine terminal. Now, we can similarly approach for the D-axis system also. In the machine, induction machine, usually we require to have a stable flux. We want to have flux which is going close to the rated value, neither overfluxing nor reducing the torque capability of the machine. So which is why we need to have a good control over IMR as well. Now, similar to the speed, we need to have a reference for the flux. It need not be provided externally, but we need to have a reference for the rotor flux magnetizing current, which is actually representation of the flux in the machine. And once again, going by the feedback control method, we are having the feedback IMR getting subtracted from the reference, and the error is basically fed to the PI controller responsible for reducing the error between the IMR reference and IMR. And since IMR is dependent on ISQ, so the PI controller for the IMR loop would be generating reference for ISD. Now once again, once we have the ISD reference, we would go for the feedback based control and we will compare the actual ISD with this, and the error will be fed to another PI controller meant for the ISD control. Once again, because we are finding similar terms available in this voltage plant also, we have nonlinear terms corresponding to the cross coupling and a term which is there during the dynamic conditions coming on account of the change in the IMR happening dynamically. So these terms must be compensated in advance, and which is why we have the feed forward terms corresponding to that. Now we will have the opposite signs used over here for these terms. And scaled by the gain of the inverter. Now it should be noted that DIMR by dt, so we can complete the loop over here. We can connect the VSD star. Now while taking the feed forward, we need to note that there is a term which involves derivative of IMR. Usually, if we want to have derivative of any quantity, it is always noisy because taking derivative basically results into noise when we are going for numerical derivative of the quantity. So DIMR by dt could be a very disturbed signal. Now one way is that we can differentiate and then we can use a low pass filter to get rid of the noises. However, we can have a different approach, which is we can take DIMR by dt from the equation provided for the computation of IMR on basis of ISD and IMR itself. So in the feed forward term, instead of using DIMR by dt, we can go for this term which is equivalent to DIMR by dt. So under the conditions when IMR is stabilized, there is no further change on that. It has reached the steady state. This term is eventually going to reach zero. Now, going ahead, the task for designing the controller is required to be taken up for this system. And we are noticing that there are several terms which are coming as a disturbance. For example, all the feed forward terms which are cancelling the nonlinear terms can be considered as the disturbance to the system. Similarly, the load torque which is applied on the system, which is not internally controlled or not internally generated, it is an external force, external torque. So many a times the estimate for this is not available, so it can be treated as noise to the system or disturbance to the system. So such terms can be ignored, and we can have the block diagram simplified by simply ignoring these terms. So we can connect the path directly. Now, looking at the system, what we realize is that we have current quantities coming within the flux and speed control loops. So for example, when we are talking about the speed control, we have the PI controller which is eventually controlling the speed. However, there is current control loop sitting within the speed control loop. Similarly, there is a current control loop sitting within the flux control loop. Secondly, we have one more level of complexity involved over here, because computation of torque is happening on basis of IMR as well as ISQ. So just by having decoupling of the inner and outer control loop, this is not going to be solved. So we need to have some discrimination between IMR and the speed control loop as well, because IMR is involved as a quantity within the speed within the torque computation in the speed control loop. We need to allow IMR to settle down sufficiently before taking any action on the speed control loop. So this gives us hierarchy in terms of the bandwidth for different systems. So we have current control loop bandwidth, can denote it by omega b omega I. We have flux control loop bandwidth given by omega b omega psi. We have speed bandwidth, speed control loop bandwidth. This can be given as omega b omega omega. Now, these three bandwidth are basically going to decide how our system is going to respond, because the current control loop is existing within the flux and speed control loop. It is very well clear that we are going to have a very clear difference between the bandwidth of the current control loop and the flux and speed control loops. However, there is no such clarity existing for the flux control loop and the bandwidth and speed control loop bandwidth. So because we are considering that our torque has to be stable, and for that the flux has to be stable, as stated, IMR must be settled much faster compared to the rotational speed. So now we can keep a limit on the bandwidth for differentiating between the different response time. So we can say that as a rule of thumb that our speed control loop bandwidth is basically 1/10 of the flux control loop bandwidth. And now we can go by defining that because our current control loop is existing within the flux control loop, so bandwidth for the flux control loop is going to be 1/10 of the current control loop bandwidth. So which means that our speed control loop bandwidth is going to be approximately 1 by 100 of the current control loop bandwidth. And as seen in case of DC motor as well as permanent magnet synchronous motor, we have given a clear understanding about how and why there should be a maximum limit on the current control loop bandwidth. So we are respecting that our voltage output is generated on basis of PWM, which is a kind of non-linear phenomena which is happening. So to ignore the harmonics which are going to appear in the system, we need to have clear discrimination between the bandwidth and the harmonics which could be generated by the system. So the bandwidth for the current control loop is considered as 1/10 of the switching frequency. So we can say that omega b omega I is 1/10 of 2 pi fsw. So this gives us some clarity on how different bandwidths are related to the switching frequency of the inverter or of the system. So this is how we are going to have, and typically if I take a number that if our switching frequency is going to be say 5 kilohertz, then we are going to keep our current control loop bandwidth somewhere around 500 hertz. We are going to have flux control loop bandwidth somewhere around 50 hertz, and we can place the value of speed control loop bandwidth somewhere at 5 hertz. So that is how the numbers may look like. There may be some relaxations under different conditions, but suitable adjustments must also be taken in the model and in the design. So having this understanding, now let us proceed with the design of the current controller first, because once we are deciding that the bandwidth is 10 times faster compared to the outer control loop, it becomes kind of independent quantity with respect to the outer control loop. So since the D axis and Q axis plant and controllers are identical, we will take a generic IS reference which is compared with the generic IS feedback. We have the controller, PI controller, so the coefficients are indicated as KPI, KII by S, and the output of the controller is basically fed to the inverter, so there is a gain, and then we have the plant, RL plant corresponding to the machine, so S sigma LS, and this results into the current. Now this may either be ISD or ISQ. The design is going to be same for both. Now taking the similar approach what we have seen in case of permanent magnet synchronous machine, we are going to write the open loop system, open loop transfer function, and we are going to have pole zero cancellation for removing the slowest pole in the system, and by rearranging the terms, we can end up in this form where Kp by Ki can be equated to sigma Ls by Rs. and we can achieve pole zero cancellation in this condition, and we can write rest of the transfer function as now. Since we have taken the condition for taken a value for the bandwidth of the system current control loop, so we can write the closed loop transfer function of the current control loop can be given in this manner, and the bandwidth for the current control loop, which is equal to 2 pi fsw by 10, and from the expression we can equate, and thus we can determine the value of ki from here, and then from this equation the value of kpi. So we can plug in these values of kp and ki in the current controller, and we can achieve the desired response from the current controller. Now, just to clarify, the gain over here, capital G, stands for VDC by 2 in case we are talking about sine triangle PWM. So that's the inverter gain considered over here. Now, once we have plugged in the value of Kp and Ki, the current control loop eventually reduces to a first order system where we have the reference given for current and output is following that reference, where tau I is inverse of omega b omega I, which can be written as, or so if we try to plot the response of this controller at a given instant, if we have the reference for current step input given for the current reference, then our current is going to follow with certain delay, which is defined by the bandwidth of the system. So this is how the response of current control loop is going to look like, whether it is for D axis or Q axis. Now once we have designed, we can use these parameters for taking up the other control loops. So first, because we are defining the next highest bandwidth for the flux control loop, so we are going to consider IMR control loop design. To differentiate, we can keep Kp psi, Ki psi by S as the parameters for the PI controller used for IMR, and then this is eventually generating the reference for ISD, which is going through its control loop, which is reduced to 1 by 1 plus S tau I. The generated ISD again goes through a first order filter, which is corresponding to the rotor time constant of the machine, and this generates IMR in the system. Now, because we have two different first order systems over here, two different poles over here, one way could be that we can combine and see the cumulative impact of these two poles. So if we try to combine these two terms mathematically, we are going to end up having and So here we have product of these two terms, and because the product of these two terms tau I and tr is going to be much more smaller compared to the sum of these two terms, so it can eventually reduce to which means that effectively we are dealing with a pole which is having time constant say tau 1, which is equal to tau I plus tr. That's an effective pole being generated by these two first order systems. So our open loop transfer function for IMR can reduce to now once again similar to what we have realized for the current control loop, we have a slow pole available in the system. We have a zero which can cancel the zero on account of the controller. So which is why we'll go for the pole zero cancellation, and we would equate tau 1 with ki psi, and the remaining term looks very similar to what we had for the current control loop. And of course there is no gain available over here. It's just a first order filter for the IMR realization. So which is why we end up having open loop transfer function given like this. So which means the ki psi can be decided on basis of bandwidth for IMR control loop. So we have and in fact ki psi is nothing but so in this manner we can come up with the parameters for the flux control loop as well. Little more complication comes when we go for the speed control loop. However, this is also going to be very similar to how we have done for the DC motor drive and the PMSM motor drive. So we have the error generated between the omega m star and feedback omega m, and for clarity we can give superscript of omega to the kpki parameters of the controller, which is eventually generating ISQ. ISQ reference is passing through the closed loop system having a time constant of tau I defined earlier, which is generating ISQ, and then we have IMR appearing along with the constant KT and the mechanical plant. So here we are considering the worst case where our friction is nearly zero. And the feedback for omega is basically taken after a filter. Time constant for the filter is written as tau f. So because of the noise available in the surrounding and it's coming as a measurement of a mechanical quantity sitting on the motor, the sensor might be sitting on the motor. So we are having a first order filter to remove all the noises so that our feedback is not affected by such disturbances. Now in this system, once again, if we try to write the open loop transfer function, it should be noted that we are treating IMR as a constant for this control loop. So we are not including any dynamics or any plant for the IMR value written over here. So this is how our open loop transfer is going to look, open loop transfer function is going to look like. And what we understand that once again we have two first order poles sitting at different distinct locations which can be combined mathematically into a second order system, and once again the product of tau I and tau f is going to much smaller compared to the sum of tau and tau f. So it can be approximated to equivalent first order system, which is sum of tau I and tau f, so which can be given as tau 2 for convenience, and the remaining open loop transfer function is written over here. So now comparing with the previous designs what we have done during this course, once again the system is found to be unstable on account of this double pole located at the origin. So we are going to have unstable system if we are only going to approach the design by having pole zero cancellation. So we need to have a different method, and we can go for once again the symmetric optimum method for designing this system. So what essentially symmetric optimum method is going to do is we are going to locate the zero and this pole symmetrically about the zero crossing of the open loop characteristic. So we'll try to draw quickly the Bode plot response of this, and then the values can be computed on basis of the conditions. So we have Bode plot for the open loop transfer function where we have the 0 dB line, and magnitude plot would start with a slope of minus 40 dB per decade because of the presence of double pole at the origin, and if there is no correction taken, this is going to cross the 0 dB line with a slope of minus 40 dB per decade, which basically indicates that phase of the system is going to be minus 180 degree, while the magnitude plot is crossing the 0 dB line. So the phase margin for the system at gain crossover frequency is 0, and that is the case where we find that the system was unstable, which means that we have to work on improving the phase margin of the system by positioning the pole and zero around the zero crossing of this magnitude plot. So we are going to locate our 0 first, before the line meets the 0 dB line, we are going to locate the 0, say at this location. So I can mark here by omega z. So if this corner frequency is reached first, then the slope of the magnitude plot is going to change from minus 40 dB to minus 20 dB per decade. And we need to have the location of the pole sufficiently far so that the magnitude plot crosses the 0 dB line with minus 20 dB per decade slope only. And later on, once the pole frequency is reached, it can always return back to its original slope, minus 40 dB per decade. So in this manner, we are going to see some improvement in the phase margin. So phase is going to start improving, and eventually it would come back to minus 180 dB, minus 180 degree. However, at the point of 0 crossing, we are going to have some positive phase margin, and that is where our system is going to become stable. Now, when we are saying symmetric optimum, the condition that is imposed by this method is that the distance between the 0 and the 0 crossing of this magnitude plot, which is also the bandwidth of the closed loop system, is same as the gap between omega b omega and omega p. So because we are talking about logarithmic x-axis, so we are going to have same ratio for these frequencies. Say that ratio can be given by A. So if we keep this ratio same, we are going to find the highest phase margin, which means the phase margin is going to maximize at the point of GCM, and hence we'll be able to achieve the best phase margin for the system. So we can write the condition that we are imposing on account of symmetric optimum method. So it's kind of a geometric progression we are now trying to have between these different frequencies. Now, this is one of the conditions that we are having for solving the values of Kp and Ki. The next condition is going to be that how much phase margin are we targeting. So this can be worked out in terms of the parameter A by taking the phase of the system, phase of the open loop transfer function. So if we compute the phase of this transfer function, we are going to find that the constant term is not going to contribute anything in terms of phase. The second order term, double pole sitting at origin, is going to have minus 180 degree contribution. The next 0 is going to have contribution which is positive, and then we are going to have negative contribution from the pole. So altogether the phase margin can be given as the sum of these two terms. And we are talking about phase margin at the gain crossover frequency. So omega can be written as omega b omega, and hence this can be simplified as tan inverse A minus tan inverse 1 by A, and this can be combined and solved in this manner. And for a good design or for a reasonable response of the system, we can have a phase margin of 45 degree taken for the system, for the motor drive. And then we can write the quadratic equation for A, and we can solve for value of A which is greater than 0, because it is essentially a ratio between two frequencies. So we end up having a number for A, and then this can be used for solving the rest of the unknown quantity. So now, once we have realized the value of A, we can always have understanding that where our frequency is going to be located with respect to what is known. For example, the pole frequency is known, so we can always say that where our bandwidth is going to be located, and then where are we going to keep our zero frequency. So these parameters can be computed. Eventually, getting the kpki value, we can impose the third condition, and that relates to ensuring that our gain crossover frequency is exactly at omega b omega, which means that the magnitude of open loop transfer function at this frequency omega b omega is equal to 1. So with these three conditions, we'll be able to solve for three unknown variables which are there: A, kp omega and ki omega. So during this process, once again, to emphasize that we need to ensure that the bandwidth achieved for the speed control loop should be 1/10 of the flux control loop. So this is all from the design point of view for the controllers. Now, because we are going to have the realization of the machine on a real controller and on a real system, so we need to have little bit more understanding about the implementation part. What we have done so far is we have computed the parameters of the controllers which are going to be used for the system. So if we try to draw the block diagram in terms of the actual system, we are going to have IMR reference which may be generated internally, externally, having PI controller implemented on one of the microcontrollers or in simulation block, which will eventually generate the reference for ISD. We have the comparison of ISD and ISD reference, and the error is once again fed to the PI controller, and it generates the reference which is basically corrected with respect to the feed forward, and the command for D-axis voltage is generated at this point. So this is the phenomena which is happening within the controller. Now similarly, we have omega reference, omega m star. We have the feedback for omega m, the PI controller for a speed control loop, which is eventually generating the reference for Q-axis current, and we are having the feedback of ISQ. This error is fed to PI, and we have the feed forward correction terms over here, which eventually generates the reference for VSQ. Now, this all computation, this all phenomena is happening within the controller, but this controller is eventually going to interact with the hardware. So we need to have the correct, say, signal which is going to be appearing in the say the PWM generation. So we are going to have dq to ryb conversion, where we will generate the three-phase modulating signals, which are eventually going to get compared with triangular carrier for generation of the PWM signals for all the three legs. So we are considering two-level VSI. So we have R top, R bottom, Y top, Y bottom, B top, B bottom. So these gating pulses are generated, which are eventually fed to the gate driver unit of the inverter. So the hardware, which can be represented with a different color, for example red, the inverter has DC supply available with it. The value can be taken as VDC, and on basis of the gating pulses given to the system, this is ultimately generating the three-phase output, which is connected to the induction machine. This induction machine eventually connects to load. Now this is how our physical system is going to look like, the entire control system along with the hardware. Now it should be noted that for achieving the closed loop control, we need to have certain feedback. So the feedback of three-phase or two-phase current from this system can be taken, IR, IY, IB, and this can be ultimately transformed to IDIQ, which are used for the feedback process for the controllers. Now once again, after realizing ISD from this transformation, we can have the model for the rotor flux given by simple low pass filter consisting of the rotor time constant, which generates IMR. Now this completes the feedback process for the current, the flux and all the things. Once we go ahead taking the feedback of the speed, there are basically two options. One, we may have some kind of speed encoder installed on the machine, which may provide us the value of omega m directly, which after filtering and necessary conversion to electrical radian per second can be fed to omega m. This method, where we are having the speed sensor available for the system, is called sensored vector control. We are having the speed encoder or the sensor available in the system, which is essentially providing us the omega m value. Now in that case, because for all the conversions dq to ryb or ryb to dq, we are going to need the unit vectors. Now these unit vectors can be generated on basis of the feedback omega m which is available, by assuming that our flux is going to be oriented along the theta generated from this omega m. So we have the omega m value generated in electrical radian per second. We can always add the slip value which can be computed and we can realize our synchronous speed in electrical radian per second, which can eventually be integrated to give rise of rho. And from here we can have the sine and cosine tables to generate sine rho and cos rho. Now this method, when we are trying to orient the sine rho and cosine rho, these unit vectors are eventually related to rotor flux. Unlike permanent magnet synchronous machine, we do not have permanent magnets or any other kind of excitation available on the rotor. So which is why, because of the symmetry in the machine or in the system, we can take sine rho and cosine rho generated by this system, and we can consider that our flux is oriented along this. Which means that we are not exactly computing or measuring the rotor flux. Still, we are providing the unit vector which is going to be responsible for the axis transformation in the rotor flux oriented frame of reference. So, this type of vector control can be called as indirect vector control. So this is basically called as indirect vector control, where we are trying to orient. We do not have the exact information of the rotor flux vector. We are generating sine rho and cosine rho, and then we are saying that yes, our rotor flux vector is going to be oriented along that. So we are considering that as one possibility, and then we are operating the machine with that. So this is the way we are indirectly orienting our system to what is available in the whole drive system. Now, the second way, we may not have any speed encoder available on the system. We can have only current sensors which are available, and perhaps voltage sensors if there is possibility of change in DC link voltage. Now in this case, the method or the vector control name changes to sensorless vector control. Now because here we do not have the measurement of omega m, so we cannot have any direct estimation of omega s, and hence we cannot have the sine rho and cosine rho generation from this process. So indirect vector control is not a possibility through sensorless vector control. So we need to have a different method of realizing the rotor flux, and of course mathematically, because it is not measured anywhere. So we need to estimate the rotor flux in the system, and then we need to come up with the unit vectors on basis of this estimated rotor flux, and of course unit vector as well as the speed of rotor as well as synchronous speed, and this method is basically called as direct vector control. So we'll see the method or the equations, how can we have estimation of rotor flux and how can we have unit vector generation on basis of that, and then eventually taking us to the generation of the speed feedback. Now once again we need to look at the equations which we have mentioned and which we have defined in the beginning of this derivation. We have defined rotor flux as the magnetizing flux plus the leakage on the rotor side. Now, because we are targeting the realization of the whole system on a realization of this whole estimation on a physical system, so we can choose a suitable frame of reference for all the quantities. For example, stator frame of reference. Now, eventually what we have basically is that we have LM IS plus IR in a stator frame of reference, LLR IR in the stator frame of reference. This can be written as IR can be segregated, which eventually can be written as LR. Now, while realizing or trying to realize the value of rotor flux, we again cannot have the measurement of the rotor current. So we need to replace this IR with suitable terms. So I am going to write IR as psi R minus Lm times of Is whole divided by Lr. Now we can write the value of stator flux, which after this kind of rearrangement can be written as LSIS plus LM IRS. So here all the equations we are trying to write in the stator frame of reference. Now, once we have this stator flux, we can basically plug in the value of IR from the previous equation, say equation number 1. Now this equation gives us possibility that we can have an estimate of rotor flux in terms of stator flux and the measured current Is. So we can simplify it little bit more. So 1 hour हो जाए तो आप बताइएगा, हाँ, बिकॉज ये थोड़ा लंबा डेरिवेशन है. हो गया है? अच्छा. Shall I continue or shall I stop? Because this is going to take another 20 minutes. नहीं, आप कंटिन्यू बोलोगे, ये लोगों से पूछना है ना, those who are doing the class. पक्का? चलो रुक जाते हैं. Okay, any questions up to this point? हाँ, again after this it will follow. That's why I'm saying 20 minutes. Okay, ठीक है? So we can stop here and then continue कर देंगे next में. 1 hour and कितना minute हुआ है और exactly 1 hour हुआ है. अच्छा. So I can stop here and then I can give this closing remarks. ठीक है? हाँ. So we will continue with the derivation of rotor flux, and we will also see how the limits for different controller outputs and the reference for IMR can be computed on basis of the nameplate rating of the machine. And this we will do in the next lecture. Thank you.